Welcome, ladies and gentlemen, to our lecture on Newton's universal law of gravitation. Today we're going to talk about Newton's law of gravitation, and then we're also going to talk a little bit about circular orbits, and we'll finish off just by mentioning the idea of frequency. So, Newton's universal law of gravitation. Newton correctly deduced that the force of gravity between two masses can be expressed this way. The force of gravity is equal to big G m1 m2 over r squared, where r is this distance between the two objects. M1 and M2 are the masses of the two objects, and then this big G is what we call Newton's gravitational constant. Okay, and we can kind of think of this as like the strength of gravity. And it's a constant, so it has the same value in all systems everywhere in the universe. Okay, so the value of G is equal to 6.67, and then Newton meters squared per kilogram squared. And you can see that it must have those units in order for this top piece to come out as a force, right? We have the meter squared to cancel this, the kilogram squared to cancel the top here, and then we get a Newton out, which is what a force has to be. Now, technically, this equation requires two spherical masses, but it'll be good enough for us even for non-spherical masses, okay? And note that gravity only cares about the distance between objects. It doesn't care about direction in any special way. It always only cares about a straight line between the two masses, okay? This is called a central force, and its effect always goes out spherically or radially. So the force of gravity always goes out like this in the radial direction. Okay? And then it grabs things out here and it pulls them in. So note also that because the effect of gravity goes out spherically, gravity falls off as 1 over r squared and not as 1 over r. Okay? So if I'm twice as far away, gravity is 4 times weaker. And if I'm 3 times as far away, gravity is 9 times weaker. And the fact that gravity acts spherically is the reason that objects with enough mass are always pulled into a shape that's close to a sphere. Okay? Gravity pulls with the same force in every direction, and with enough mass, an object will smash itself into a sphere due to the gravitational force. One more interesting thing to note about this is that when I have these kind of spherical objects like this, if I draw a circle around this one, and I'm outside the kind of circle, so in the Earth's case, if I'm outside kind of the Earth, the way that gravity works, like if I'm right here, it'll always work as if all the mass is in the center of the object here. So r will always be this distance here, okay? And this allows us to always calculate this gravity using Newton's universal law here, using the two center of masses of the object. Okay, so gravity will always act based on the distance between the center of mass of the two objects, so long as we're outside the object. Okay? It turns out that because I can always take, if I have some mass, I can always draw a circle around it, and then gravity will act as if the mass is in the center of that circle. It turns out that if I take a planet and put it in here, then out here it acts, the gravitational pull will always act like it's between the center masses of two objects, okay? But if I were to go inside, so if I imagine the Earth as hollow, if it's a hollow shell, then inside the Earth, I'm only affected by gravity that's inside of me. So if I'm here, if there's some mass in here, I'll only be affected by this gravity. This stuff on the outside won't matter. And the reason is because if I'm in some spot, let's put me here so it's a little easier for me to draw here. So if I'm in some spot inside this shell of the Earth, if you think about tracing out an arc behind me, all of this stuff goes together to kind of pull me this way, right? But then as I take that arc out here with straight lines, you see that over here there's stuff that's further away, but there's more stuff, right? And if this shell is equally thick all the way around, it turns out that the amount of stuff over here pulling me this way, once I take into account this distance between it, creates the same force as the amount of stuff pulling me this way once I take into account the distance between me and that stuff. Okay? So inside of a shell, if I had just a shell like this of the Earth, or if I had a hollow area in the middle of the Earth, I would actually be weightless in here. I would feel kind of a micro G or a zero G environment, just like I would when I'm in orbit around the Earth. Okay? That's a cool little thought experiment that comes from carrying out the implications of Newton's universal law here. The truth, though, is that planets aren't hollow in the middle. Earth isn't hollow in the middle. So this isn't going to happen for us, right? So that's the only time I'm going to talk about it. It's just an interesting little quirk of gravity and the way that it works, the fact that it works spherically. But we're always on the surface of the planet. And so standing on the surface of the planet, this force is always going to act like the center of mass of us is pulled by the center of mass of the Earth. Okay, and the R then is going to be the radius of the Earth generally. So now let's take a second and talk about big G and little g. Okay, big G is Newton's gravitational constant. That's the one that's the same everywhere. 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Okay? Little g is what we've been using before, and that's the acceleration that an object has near the surface of the Earth. Okay? So that one has a special area that it applies, right? Near the surface of the Earth. So don't get them confused. They're very different. This one is a universal constant. It's true everywhere, all the time. This one is an approximation for objects near the surface of the Earth. Now, when I told you that little g was 9.8 meters per second squared, I told you we'd eventually talk about why little g was this value, right? And why it was the same for all objects near the Earth's surface. And Newton's universal law of gravitation gives us the tool that we need to talk more about this, okay? So let's consider an object near the Earth's surface. We have the Earth here, and we have some object that's near its surface, okay? Let's even put it closer. All right? Now, we were talking about gravity always acting between the center of masses, right? So let's calculate the gravity using Newton's universal law. Okay? So the force of gravity between some object and the Earth is going to be big G, and I'm going to use big M for the Earth and little m for the object. Okay? So it's the Earth's mass times the object's mass, and that's over the radius, or the distance, r, the radius, between the center of masses of the two objects, okay? Now, if the object is near the Earth's surface, we can just call that the radius of the Earth. Because if it's the radius of the Earth plus, 100 meters, that's still basically just the radius of the Earth, okay? The radius of the Earth is equal to 6.37 times 10 to the 6 meters, okay? So 6.3 million meters. So 6.3 million meters plus 2 meters is 6.3 million meters, right? So that's why we can say that the force of gravity between the Earth and some object that's near its surface is this quantity here. Now, this starts to give us an idea about why we say near the surface of the Earth. So what does near mean? Well, near means that we don't change this value very much, right? So you can see as we start to get to, say, 10,000 meters away, well, then we're starting to change this digit right here, right? And then it might start to change our answer a little bit. If we're 100,000 meters away, well, then this guy right here is going to start to change, this digit, right? And now maybe we really start to see something. And if we get to, say, 1,000,000 meters away, well, now we're really changing this radius by a lot. And that's really going to change the force of gravity between the Earth and the object, right? So when we say near the Earth's surface, what we're really saying is that this radius of the Earth changes by a small enough amount that the change is unimportant, okay? Oh, I forgot the square down here. This is squared, right? So that's the force of gravity between the object and the Earth. Now, remember, when something's in free fall, it only has gravity acting on it. So the sum of the forces on the object is just Fg. And then, of course, that's equal to the mass of the object times its acceleration, right? So now that we have an expression for Fg, we can put that in. So for some objects, we haven't even said what it is, but for some object near the surface of the Earth, this is the force of gravity. And then that's equal to the object's mass times its acceleration. But you can see I have the object's mass on both sides, so it cancels, right? And that means that the object's acceleration is equal to big G times the mass of the Earth over the radius of the Earth squared. Okay? That was a totally general derivation, right? That was for any object near the surface of the Earth. We never said what little m was. It didn't matter what it was. I ended up with this acceleration. But look at this acceleration. It doesn't depend on any property of the object, right? It depends on big G, it depends on the mass of the Earth, and it depends on the radius of the Earth. Those are all things that don't have anything to do with the particular object, okay? That's why all objects end up with the same acceleration, because when we had this equation here, the force of gravity between the Earth and the object made a difference, depended upon the object's mass, right? We know that things have different weights. The force of gravity between the Earth and some object is the object's weight on the surface of the Earth, right? We know that that's different and that it depends on the object's mass, okay? A bowling ball and a beach ball have different weights. The force of gravity between the Earth and those objects is different. But we also know that an object's inertia depends upon its mass, okay? So when we give an object an acceleration, the acceleration is smaller for bigger masses, okay? This side is the dependence of the object's inertia on mass. And the fact that the force gets stronger, directly proportional to the mass, and the inertia gets stronger, directly proportional to the mass, well, this means that A over here doesn't end up depending on the object's mass, okay? Because the amount that the force of gravity increases is the same as the amount that the inertia increases as we increase the mass. And then, of course, this A near the surface of the Earth is actually little g, right? And if we plug in numbers here, okay, we have g up here, we have the radius of the Earth here, and then the mass of the Earth is equal, and we'll use something a little more precise than what I sometimes use. We'll say 5.972 times 10 to the 24 kilograms. So if we plug in all those numbers, what do we get for this acceleration near the Earth's surface? Well, we get little g. We get 9.8 meters per second squared. And that's why every object has an acceleration of 9.8 meters per second squared when it's near the Earth's surface, okay? We figured out what near means. Near means that this RE squared doesn't change by too much, right? It doesn't change by an amount that's large enough to make this start to be noticeably different, okay? That's why this little g is the same for every object, because in this equation, the object's mass was on both sides, okay? Affecting both its inertia and its force of gravity. And then the values of the radius of Earth, the mass of Earth, and big G are the reason that the acceleration has this value 9.8 meters per second squared. So now we understand little g a lot better than we used to. It also shows us why we can get an object's weight from mg, right? So if little g is equal to g big M over radius of the Earth squared, then when we take mg, we're multiplying that by m, and of course that is the force of gravity. So that's why our weight, when we do these force problems and we're considering stuff on the surface of the Earth, that's why we can just use mg for the weight of the object, and that equals the force of gravity. The other thing that comes from this is, notice for the radius of the Earth, we used just the average value. We use the average radius of the Earth, assuming the Earth is a sphere, but the Earth is not actually a perfect sphere, right? The Earth, if this is the Earth, the diameter of the Earth is a little bit longer at the equator than it is from pole to pole, like this, okay? So it's a little bit, I'm going to draw it exaggerated here, but it's a little bit football shaped like that, okay? And that means that little g, because this is 1 over r squared, ends up being just a little bit smaller at the equator than it is at the poles. So the value of little g actually varies by a tiny bit depending on where you are on Earth, but that variation is generally small enough that we can ignore it and it doesn't really change our answers much. So we end up just using an average radius of the Earth, okay, or the radius they would have if it was a perfect sphere, and using this constant value of little g, okay? But remember, little g is an approximation. It's not a universal constant, okay? Big G is a universal constant. This has a value that just never changes. That's just a property of the universe, okay? Little g is an approximation. It's not actually a constant. We just treat it as a constant because it varies by a small enough amount that generally for our purposes in any given problem, we don't really care how much different it is from 9.8. So now we know all about little g, and we used Newton's universal law of gravitation to learn a lot more about little g, to understand it a lot better. But let's go back to just Newton's universal law, and let's look at circular orbits now with this new tool. Okay? In a stable circular orbit, okay, like let's say the Earth is in uniform circular motion around the sun, gravity is always providing the exact amount of force required for the centripetal force of uniform circular motion. Okay? Remember that if we have uniform circular motion, our acceleration is pointed straight in. Okay? And that means, through F equals ma, that the net force also must be pointed straight in. Okay? And we have some force of gravity, Fg, pulling this object in this way. And so the force of gravity we just learned is equal to big G mm over r squared, okay? And for uniform circular motion, if one object is going to more or less sit still and the other object's going to orbit around it, we have to have one mass that's way bigger than the other, right? Because if we don't, the two objects will have, if they have inertia that's similar, well then when they pull on each other with the same force, they're going to have similar reactions to that, okay? And so then you end up with a situation where two objects orbit around each other and they both move all the time, like with some binary stars and things like that, okay? Or even, I think Pluto and its moon are of similar enough masses that they kind of tend to orbit around each other. So this situation is not what we're considering here, right? We're considering a uniform circular motion where we have one object that's so much smaller than the other object that the one just kind of orbits around it. Just like you're so much smaller than the Earth that when you push away from the Earth, when you jump and things like that, you don't move the Earth, right? But the Earth moves you a lot. The same thing is true with kind of the Sun and the Earth. The Sun just kind of hangs out and the Earth is in a pretty circular orbit around the Sun. So for that to be true, to have this uniform circular motion, we know the only force on this object is gravity, okay? And we know that it has to have a centripetal acceleration, v squared over r. And so that means that the mass of the object times v squared over r, the centripetal force, has to equal the gravitational force to have a circular orbit. If it wasn't equal, and it pulled on it too much, then what I would have is, instead of going in a circle, I would be getting pulled in at the same time, right? So instead of just going around in a circle, I would spiral inward because it would be pulling enough to turn me, right? But then also enough to keep pulling me in as I go around, okay? So to maintain a stable circular orbit, it must be true that this centripetal force is exactly the gravitational force. Now this means that this equation tells us how fast an object must travel in order to maintain a circular orbit of some radius, right? So if I solve this for v, I would get that v equals gm, the mass of the big object, over r, all in a root. Now let's check it real quick. That was Newton meters squared over kilogram squared, right? Kilograms over the r is meters, okay? That's equal to, a Newton is a kilogram meter per second squared, meters squared, kilogram, and then on the bottom the kilogram squared meter, okay? And then the kilograms all cancel. This meter and this meter cancel. I get meters squared per second squared. Remember, this was all in a root the whole time. And I get meters per second. Okay? So we didn't screw anything up. This is working by dimensional analysis as well. So you can see that my velocity for a circular orbit is different depending on the radius, because g and big M aren't going to change as long as I keep orbiting the same thing. So if I'm always considering objects orbiting the sun, the bigger this radius gets, right, the smaller my velocity is. So if I'm in here and I want to maintain a circular orbit, I have to be going faster than when I'm out here and I want to maintain this circular orbit. Okay? And then again, if I'm even further out, if I'm way out here and I want to maintain this circular orbit around the sun, I go even slower, right? As the radius gets bigger, I have to travel slower to maintain this circular orbit. And objects that are in orbit are always in free fall. Remember, we said free fall was an object with only gravity acting on it. Well, this is true of objects in orbit, okay? They always have gravity as the only force acting on them, so they're always in free fall. They're always falling toward the object they're orbiting. And remember, the acceleration is directly toward the center here, right? So this looks just like free fall. The difference is this velocity that I have that's tangential to the circle here. It's big enough that my velocity keeps me falling kind of around the object. So I'm always falling at the object just like any other object in free fall, but my velocity is big enough that I'm always missing the object, okay? And these two things balance out when I'm in orbit, when I'm in a stable orbit, and I end up just going around the object indefinitely, okay? And the altitude that I want to maintain this orbit, or the distance from the center of the object I'm orbiting, dictates exactly what this velocity must be. And we tend to have things settle into these circular orbits because they have some velocity. And over time they settle into this orbit that has a certain radius because they have a certain velocity. So the last thing I want to mention today is I just want to briefly talk about frequency. All right? When we talked about uniform circular motion, we mentioned the period. which is 2 pi r over the velocity, right? And that's the time for one full revolution. It's the distance, of course, divided by the velocity, which gives a time. Frequency is the number of periods per unit time. And we actually saw this when I showed an example about using a sling. We had revolutions per minute, or RPM. A revolution is 1 period, and this was how many periods per unit of time. In this case, it was a minute, okay? And the basic unit of frequency is the hertz, abbreviated Hz. And this unit is 1 over second, or second to the minus 1. So in fact, the frequency is 1 over the period, okay? F equals 1 over t. And we can see this relationship easily if I think about a very simple example, okay? So if I think about traveling in a circle, and it takes me 0.5 seconds, okay? That's the time to complete one full revolution, okay? That's the period. If I took 1 over 0.5, then the frequency would equal 2 hertz, okay? Or 2 revolutions per 1 second. And if we think about our 0.5, well, in 0.5 seconds, I'll be 1 time around. And then in 1 second, I'll go around again. That's 2 times around, or 2 hertz, okay? So this simple example shows or illustrates that frequency is 1 over the period, okay? Unit-wise, of course, we would have frequency should be 1 over second, and period is second, so 1 over t is 1 over seconds, okay? And that's really all I want to talk about with frequency today. Frequency is just really related to the period, so if you already understand the idea of a period, the time that it takes for one revolution, frequency is just a different way of thinking about the same thing, okay? Instead of thinking of the time for one revolution, we think of something that's in this periodic motion, okay? Or motion that's in periods where I repeat the same thing over and over again. The frequency is just how many times I repeat that thing per second, okay? Or per unit time. In revolutions per minute, it was how many revolutions I made in 1 minute, okay? In other applications, it's going to be how many times we complete some period per some unit time, okay? Oftentimes we have hertz, which is how many times we complete a period per second, okay? Or how many periods we complete per second. And we'll revisit frequency much more heavily when we talk about periodic motion and waves. And you'll have some homework that'll give you a chance to look into circular orbits a bit more. But for now, I just want you to know this relationship right here. Frequency is 1 over the period. All right? And that means that the period is equal to 1 over the frequency, right? So keep those in mind, and when you see things like revolutions per minute or something like that, just remember that what we're talking about is a frequency, and then that's directly related to the period, so that when you're dealing with uniform circular motion, you can then use the period here and figure out things like the velocity or the centripetal acceleration, things like that.